Good morning, everybody. My name is Alessandro Schiavi. I'm a researcher at the National Institute of Metrology, and I'm the moderator of this webinar today. I will present Douglas Valerio, that's from Mason Industry. That is Mason Industry because it's a company that established in the United States. And as you will see during the webinar, this company is especially devoted to the design and the realization of very performant and advanced system especially for vibration insulation in building in very particular situation. And in this case, we will see in particular presentation regarding the retrofit building isolation with a focus on a case study of Cambridge House in London, United Kingdom. And the presenter is Douglas Valerio, that is here with us. And so I let the floor to Douglas to begin his presentation. And after this, we can have a debate, or you can ask some question using the chat. So we ask to the auditory to write a question in the chat, and so we can turn the answer to Douglas and other colleagues to clarify everything you want. So please, Douglas, the floor is yours.
Very good. Thank you very much, Alessandro, and thank you to the Italian Acoustical Society for the invitation to present PowerPoint program on the retrofit building isolation at Cambridge House in the UK. We'd like to start off by giving an idea of what the construction site looks like. On the left is building 1. Beyond that is building 2. And the third building is on the right-hand side. And based on their proximity and varying proximity to the underground system, there's different requirements for vibration isolation. This is the facade of building 2, which is a historic facade, and it is also isolated. And we developed specialized structural brackets that control the vibration that gets into the facade. This is building 3, and the beauty of building 3, it was the home of the Prime Minister and his offices at one point in time. I'm sharing the Italian translation of the excerpt of our discussions on building isolation, and I hope they are completely legible to you today. We did our best to clean it up so that it would be readable while on everyone's screen. The most important step is having an understanding of what we do and why we do it. And one of the key components in any of our designs is the discussion of creep, discussion of safety factors related to the structural design, and how we achieve that through the proper design of our bearing pads. I won't go through this in too much detail. However, shear pins are a proprietary design, as are shear keys, and that is terminology that we uniquely use in the installations. It evolved when we started doing this in the mid-80s, and our first project was Trinity College dormitory in Dublin, Ireland. Interestingly enough, because the isolation plane is normally elevated just above the first floor, what happens is elevators need to be properly isolated as well so they don't transmit through the structure. And this particular schematic shows the installation for an elevator isolation system. This is a typical shear key. And that's another typical shear T. And there's the design. Here's the bracket that we would normally design and utilize for elevators. So there are critical components that in our over 40 years of doing this, we've actually become quite good at understanding where the problems will occur, and therefore we have the ability to circumvent those. This is our production facility in New York, and this is as Cambridge House was being manufactured. So that's a 4-cavity mold, and that allows us to produce 4 times the number of pads in each heat. Each heat lasts about 2 to 3 hours, depending on thickness. And the reality is, if we can produce 4 pads in that time frame, it's a much better system. We preheat all our bridge-bearing materials to facilitate a faster heat, and you can get an idea from the construction of the molds, the pressure that they have to handle in order to vulcanize the rubber. So it's a long process, and we believe that each pad probably takes at least 6 hours from start to finish and through testing. We independently test all our bearings in our own testing facility. That's a press that we have that's actually been rebuilt now. And the testing process occurs here, and that is a bearing that is actually perfectly loaded. We have uniform deflection of each layer in the vulcanized product, and we test them to 225% of their rated load, for the simple reason that we want to try to force a failure. And the idea is that failure could occur at any time. So if we survive 225% of design load, then we're confident that we can always write a 100-year guarantee. And that is typically what we were asked to do on building isolation projects. Here's an approved bearing with its part number and code, 4x4 by 79 millimeters high. This is a cutaway shot of the actual shear key that was installed in the new construction at Cambridge House. And the new construction had the lesser requirement of a 10 hertz design. So the bearings are a little bit less thick in building 1. And this is a vertical key, and you'll get a better idea of what that actually looks like from the ground level. This is all visible because it's in the underground parking area of that building. So what we're doing with the shear key and shear pins is handling horizontal load. So regardless of where the building is located and the fact that it's in a metropolis and there's large buildings all around, they still have the wind load requirements from storms, and they'll handle wind loads up to 160 kilometers per hour. So we have to design for that and maintain the proximity and location of the isolated building above, and handle those loads, which we transfer to the shear keys and to the shear pins. These are the actual Cambridge House drawings for those shear pins, and you can get an idea from this particular drawing the level of design and involvement that we potentially have. We'll talk about the design team and how we get involved with the design team. And while we're a supplier, we act and work very closely with the design team to achieve the proper design for not only the vibration reduction, but also the constructability. We are very concerned about any contractor getting involved in a building isolation project because it's rare. Most people haven't seen it, most people haven't done it. It takes a lot of education. In a paper that's attached that I wrote for and presented at the Australian Acoustical Society in 2019. It's a deep discussion regarding how the design team functions and what we perceive our role as. And we view our role as kind of the police at the end of the day, because we spend up to 100 site visits making sure that the contractors get things right. So the clarity of a drawing like this for the construction of a shear key is critical to the success of the project. These are shear pins attached to a beam, and the bearings haven't been put in yet. But what we do with shear pins in this particular instance is lock up a beam that supports the walls above the isolation plane, where there's a fairly large moment being generated by the length of the beam. In this picture, you see pads at the perimeter of building 1, shear pins and partial reinforcing being installed. There's a lot more reinforcing that has to go in. And on the left side of this drawing, or this photograph, is the actual street that you saw in one of those earlier pictures. Another view, coordination is critical. Photographing and referencing site visits are critical, and we work to make sure that we are checking everything. And it varies from the plumbing services, the electrical services, the heating and cooling services. We have to be involved so that transmission of vibration through the structure is mitigated as best as possible. This is that beam. This is the area where we were showing you the shear pins before. And these beams support the structure because that is a parking garage below, and they needed to extend the building and build the building above. So we do get involved in many aspects of the construction, and it's why it's so integral to the success that we work with the design team almost from the beginning. Once the concept is approved and the architect starts to generate drawings, it's our desire to be involved as much as possible. This is a picture of a bearing that's probably seen 80% load in the new facility or the new construction. And its uniform bulging means that we're achieving the requirements of the design. If it wasn't a straight line here at each shear plate in the pad, then what would happen is you would have a major bubble that spans the tube that you see here now. And that would mean we would have a failure of adhesion in the bearing itself. So there's a lot of things that we look for through the inspection process. There's a lot of things we educate our representatives to look for in the installation and inspection process. And like I said, it's probably 100 visits on any job. That is a fire protective coating that's been applied to the bearing, and it's normal on all of construction that fire protection becomes a discussion, and it's achieved many different ways, and it's applied many different ways. And this is a spray-on, paint-on fire protection that was used at Cambridge House. This is a good picture because it shows that the shear pin next to the bearing, and this is the shear pin, is installed. It's got a resilient membrane around it, and it's buried in the concrete, and that's designed to handle the horizontal load. The bearing is seeing partial load right now, so you see a little bit of the bulge in the internal plate, an adhesion of the internal plate. It's not one bulge alone, and this bolt gets removed or adjusted so that it doesn't short circuit, but it maintains elevation during the construction process. This is the building joint that is between building 1 and the 400-year-old building 2, and it was filled with styrofoam, construction debris, and a number of other things. And Lee, the acoustical consultant, picked up a problem along this wall when they were doing acoustical testing. And the bottom line is, we requested that they remove all of the debris and styrofoam and clean it up so that we could achieve the acoustics requirements for the project, and that was done. And there's another picture that we have that shows the cleaned up area, but it doesn't make sense to show you that. And if you read the orally acoustical report, you get a better understanding of the level of testing that they did and the understanding that we have that we got the job done correctly. This building was designed for a 10 hertz isolation natural frequency, and the building that it's adjoining to, the 400-year-old building, is designed for a 6 hertz natural frequency. The reason for that is proximity to the rail line. Here's a portion of the isolation system that was installed in the 400-year-old building, and the design and structural integrity of the upper lintel and the housekeeping pads and everything else was all in our scope. We worked very closely with the structural engineer. You can see the uniform bulging of the bearings. The gray material on top of the bearing is actually grout. It's high strength grout, and that grout buries the hydraulic adjustment that we had in place, and that becomes a permanent fixture in the isolation system because there was no way to pull it out. That hydraulic bearing and its adjustment allowed us to load the bearings while the building was still being supported structurally, not by our bearings. So you can get an idea of the complexity of an installation like this and working with 400-year-old walls that you don't know if they're going to crumble. That's a better view. This is the plugged hydraulic hose location, and that's all grouted in because it's got to become a permanent part of the installation. Can't pull it out. If you look, you see uniform deflection and bulging in the bearing itself. And the biggest issue in this part of the process was getting the correct loading. And you can see from the uniform deflections and the continuity of the deflections between the 3 bearings in this picture, you can realize that the structural engineer had gotten it right. But it took a lot of discussion with the structural engineer because they wanted to have factors of safety built in. And to achieve the acoustical requirement, you have to work within the factors of safety, but also know the actual loads themselves. And we achieved both. So not only do we have the design deflection being achieved, but we have the structural integrity. And again, we get asked to write 100-year guarantees for projects like this, and it's not a problem as long as everything is done correctly. This is the 400-year-old building as well. It's the basement level. It's where the bearings were in the portion of the building. The isolation plane, or the location of the bearings, did change levels throughout the project, and that made it a much more complex project to supervise and maintain the integrity of the design. But this is what they had to do to begin the process of pouring the housekeeping pads and the lintels so that the bearings would be inserted. So there's a lot that went into the design and construction, and our involvement and our agents' involvement was critical to the success. Is another photograph of an isolated 400-year-old wall. In one location, not this one in particular, it was over 1 meter thick and it was filled with straw. So the loading that we originally supplied meant that we had to remove some bearings because they weren't deflecting enough. So in the grand scheme, there's give and take, and there has to be a relationship between ourselves and the design team to get things like this sorted out. Here's another good photograph of the lintel and how its thickness and how those bearings operate. You can see a little bit of leaking of the hydraulic fluid into the high strength grout. But again, you have continuity and uniform deflection, and that is absolutely our goal every time. The isolated facade used an arrangement that was push me, pull me. It's the second time we've done a facade in the UK of significance that's historic. So the Historical Society in London will not allow the removal of such a facade for new construction. They would prefer that it gets maintained, and they will insist that it gets maintained. But if there's an isolation issue, then obviously floating that facade and isolating it and structurally supporting it horizontally and vertically becomes our job to do it with isolation materials. And it's just another high level of involvement to guarantee that that facade, after so many years, isn't going to come down. Is a view of how it's supported. So the building, that's building 2, and to the left of that is where those 400-year-old walls were. And this is all going to be a hotel at some point. And it still isn't finished, but it's getting there. This is building 3, and it's the former Prime Minister's offices and the location where the Buckingham Palace Guards and barracks used to be. So the idea of preserving the integrity of this, even though it's going to be a hotel, makes complete sense. So Buckingham Palace is probably less than 3/4 of a kilometer from this location, and it's walking distance. So the reality is they're historic locations and they're being converted, and because of the subway line or the underground rail line that services Knightsbridge, all of this was isolated because it's going to be a 6-star or 7-star hotel. That's the building 3 at the start of construction and the renovation. Again, the most critical components that we have to work with is getting the right load data. So you're dealing with old buildings, and this one's 250 years old, but the idea is you're trying to get as much information as possible. You're attending the structural meetings, you're attending architectural meetings with the idea that the performance of the isolation system that's costing millions of dollars to install has to be done right. And it is all of that time commitment that both the acoustical community, ourselves, and everybody involved in the design have to commit to. So I would say I visited this project from the US at least 5 times, and our agents were there probably weekly and sometimes bi-weekly. So the number of visits is a critical one to include in the bidding process. And it's also a critical number for the consultants to include, because everybody's eyes being on the project is an important step. So in my own cryptic notations, B1 is building 1, it's new construction, NC, and the isolation system is 10 hertz. Building 2 is existing construction and facade, and the isolation is 6 hertz, and the same applies to building 3, and that's the park in front of Kensington Palace, right in front of you. So there's a lot going on. There's a lot of eyes on it at all times, and the biggest issue is just getting through all the detail. The amount of detail involved requires a tremendous effort. And here's a typical drawing where there's part of the isolation system that's elevated beyond the existing system and how we're going to treat it. And that's how we treated it. And all these details become significant because people are going to ask the questions and they need to have engineered answers. So you can see we've got acoustical hold downs here, with the idea being that there's going to be overturning moments generated, and they have to be designed for. Here's an elevator pit where we also have to do additional design, but it's isolated. Again, it's the lowest portion of the building that's accessible by the public. So that elevator pit has to be isolated. And here you have multiple shear pins and multiple bearings in the pit designed to handle the load of the elevator and the shear walls, with the idea that we're not going to transmit any vibration from the structure above the isolation plane. So this is a different level of the isolation plane, and all the joints have to be resilient. Everything has to be taken into account to get the job done right. Details of all the elevator pits and some additional details on the product. These shear pin drawings are critical because you want to make sure everything gets installed and isolated properly. And the idea is supervision on the site ensures that not every contractor or construction manager is going to know what to look for in these situations. And it's important that eyes are on everything. This is an overview of the new building, that's building 1. And the idea is, we're just engineering and giving bearing layouts like this one on building 2 that allow everybody to understand the complexity of what we're doing. That's work in progress as of September 28th, 2022. And it's all part of the process that the inspections are done. There's probably 100 inspection reports that are done by the agent Mason UK, with the idea being that there's a history, not only in writing, but a photographic history of the inspection that gets submitted on a regular basis, with the idea being if there is a complication, maybe we can spot it after the fact if there is a noise problem. And it was the same related to the oral lead test that was done building 1, building 2 expansion joint, where it was filled with debris. So you have to have your eyes on everything at all times. This is the acoustical report for Deconstruct UK for building 3 compliance. And it's just important to understand that they're going to go through the process. I believe in the executive summary, they'll basically explain that we've achieved the requirements, but additional testing may be required to ensure that the entire building achieves the result after construction. So it's quite common that acoustical testing is conducted before to establish the natural frequency of support, during to establish whether there are any short circuits or compromised locations, and after to ensure that the client receives the design and intent of the isolation spec. So there's a lot that goes on. I won't go through the report any further than necessary. If anyone has questions, we can circle back to the report, but it tells you everything that's going on. This is a paper which is titled A Practical Approach to Building Isolation, which was written and presented at the 2019 Australian Acoustical Society meeting. And it addresses the design team and how everybody needs to work together. It addresses, the design and the functionality. It addresses our engineering experience, so you can see shear keys there from other projects, in particular Bond Street in New York. And I've included a full set of drawings for Bond Street for everyone to view, to see the input that is provided. Long-term creep is a consideration of every one of these projects. And long-term creep is the only thing that can compromise the design over time. Any and all investors and builders and building owners and developers are going to want some kind of guarantee. We've given 25, 50, and 100-year guarantees depending on what the client is looking for. We've probably issued over a dozen 100-year guarantees. And what's required to achieve a 100-year guarantee is the intent was met, the contractors were careful, the supervision occurred, the sign-offs occurred, and the structural engineer provided the correct load information. And I highlight that component because too often there can be too great a debate at what the loading is, but we like to understand the actual load, we like to understand the design and operating load, and we like to understand the critical overload issues. Normally, if we're involved in the design, we'll design at 80, 100%, and 120% of design load so that we can have a range of natural frequencies of isolation so that all of the isolation occurs within the parameters of the specification between 80 and 120% of load. And that's our way of ensuring success. Again, this is the shear pins. The discussion of shape factor is critical because shape factor is the requirement for designing for overload and stress. And the idea is low stress, low strain means that we can achieve these 100-year guarantees. This is a creep curve. And the idea of creep test shows you how little additional deflection is due once the loading is applied. Typical analysis of any of our load deflection curves is going to be by drawing a tangent at the apex of the curve. And the idea of that tangent being there is it lowers the actual deflections so that we know that we're achieving everything by design. So the process is rather involved. After doing it for 40 years and being involved in some significant construction globally on 3 or 4 continents, I'd have to tell you that we have the in-house knowledge to get all of this done. When we have any issues, we have licensed structural engineers, mechanical engineers, and civil engineers on staff. So we can do almost everything in-house. However, all of our testing is done in-house, but we also employ independent testing companies to check product in the course of production, with the idea being that in-house testing is one thing, but what does an independent entity have to say about the same thing? And by using the two steps, we ensure that we are getting it right. If you haven't realized it yet, there's no mistakes allowed in building isolation, and there's really a lot of time and investment involved in any retrofit job. And we're the only ones in the world at this stage of the game who retrofitted a 400-year-old construction. So it's pretty important stuff. The conclusions in the report itself are self-explanatory. This is a set of drawings that we did for the Bond Street Hotel in Brooklyn, and the subway line passes right through here. So the real interesting component with this project is the transit authority and the city of New York requires that no horizontal load gets transmitted to the structure, and we had to have sliding bearings with acoustical stainless steel sliders installed so that we only induced a vertical load to the structure. And it was one of the complications of this project. If you're familiar with Brooklyn, New York, it's right near the new Brooklyn Nets arena, walking distance. And this is a typical sliding bearing. And I mention it only because the design requirement is to transmit no load. So we had to test the force of friction required to move the bearing under load and multiple other things. I'm gonna blow this, Oscar, can I blow this up right now or no? No. Okay, so you have the design load requirements right here where we have the 80, 100% and 120% design criteria. And that's typical of what we supply. The set of drawings involves all the critical locations. We've got walking columns that we isolated over here, so they had sliding bearings as well. And the idea of having the walking columns isolated and as sliders meant that we weren't going to overstress the concrete structure. Typical drawings, typical details, typical investment of time. These are prevent overturning moments from being generated, and they are at the shear key locations, a couple other locations in the building. But the idea is to design everything, get it fabricated so that it's uniform, have construction tolerances as best as possible, oversize the requirements slightly, but enjoy the construction tolerance that are the bare minimum, and that's 3 millimeters. You can't get any tighter tolerances than that on a real construction site. So part of our role is to manage constructability and to also gain the approval of the contractors for the way we're designing stuff. So the reality becomes the easier we make it, the easier it is to fix it if there's a problem, and everyone appreciates it. These cast in place rods were off in one case in this particular project, and because we were slightly over designed, we were able to just cut 1 or 2 of them out that were severely or incorrectly located and impossible to get right. So the idea is it's a little bit of over design, but not too much, and constructability is key. These are the shear keys. And again, attention to detail is what we're all about. You can't get into this without having that attention to detail and paying great attention to the engineering required to make sure it's all right. Again, multiple shear keys, multiple designs, and these were the limit stops that were utilized to prevent collapse bearings from occurring in the event of a fire. So there's absolutely so much involved. The design team here, there's 65 engineers in our employ, and we design all of this out of the New York office. If you haven't realized yet, we have sufficient facilities globally. We own factories in Thailand. We moved a factory from China to Thailand recently. We have the ability to manufacture like product in both locations. We have over, I don't know, 300 meters, 300,000 square feet of fabrication and office space here in New York, and about 50% of that in Thailand. So without looking at multiple shear keys, this set of drawings supplied for one reason, to show the extent of the detailing required to get the job done correctly. I think the time now is, what is it, 2:45, 2:15? 2:15 in Italy, and I would open the floor for questions, if that's where you would like to go. If anyone has any questions, I'm here to answer them. We'll take down the, yeah,
Okay,
great.
thank you. Thank you very much, Douglas, for your very interesting, let me say, impressive presentation for the work you do in London and in other buildings. So I ask to the audience if there are some questions, and I ask gently to write the question on the on the chat in the online. And so I just suggest you to take in hand the handbook that show us Douglas. That is very, very interesting from Mason industry. Is a very, very good, interesting, a very in-depth. Is a handbook with a lot of exemplification of their solution, the Mason propose, and so on. So. And is available also in Italian, so it's very, very, also from the technical point of view, is very detailed and with a lot of scientific and technical points, very, very, very clearly detailed in this handbook. And at the moment, I have not open question. I have a lot of questions, and I start waiting for question from the audience with one of my question, because you talk about that your work with architects and builders to design and to project the installation. So I mean that if you are able to provide the wall project or design of your installation, for example, if you have to put some insulating system, for example, I think I have some example in Italy, for example, for historical site or very sensitive site. So you have, of course, to install your insulation system in very sensitive or below, under very sensitive monuments, for example, and so on. You are able to work with proper engineering, or that are working as consultant or work with you in Mason, so to provide the wall project, the wall design of the installation?
So we have always acted as a knowledgeable engineering manufacturing company. We are never a consultant, but we'll explain to you how to do it. We don't bill for our service of design or education. We happen to know we have a lot of information about a very unique part of engineering, the isolation of buildings and railways. The intent is to educate to the point where we can provide enough information and enough clarity of information so that we get introduced to the design team to overcome all these unique little components that can make a job terrible. Yeah. So we're looking out for ourselves, but it's not a fee that gets put into the process. We know the process. If an acoustical consultant says, I have a potential monument that needs to be isolated, and there's a new train line that's going to be installed nearby, what would you be looking for? That starts the process. We'll explain what the critical components are and how to define them. Then we'll also work with the architect once schematics are initially drawn, and we'll try to become that integral part of the design team, but not a paid part of the design team. We're only interested in one thing: success of the installation. You know, so it is a unique role that we play. There aren't many people. I mean, I bring up the competitor's name, Gerb. Gerb is also in this business of building isolation. They are a qualified supplier. They're going to act the same way we are. And they're not going to request money, to the best of my knowledge, for their design input. And they'll also become an active part of the design team, all with the idea that it's the best way to get the job to progress. For us, it's the sale of the bearings that at a competitive price that can be built. That's it. You know, when I say the design team has to have literally 50 or 100 visits from us, that's part of it. You know what I mean? That's an important component to compensate for. In the paper to the Australian Acoustical Society, this discussion of those practical aspects that are so critical to achieving success. But again, we're not a paid consultant. We're all professional engineers. That's a separate issue.
Okay.
You know? So commercially, we're not trying to design for a fee. It's never the process, and never would.
Thank you. It's clear.
Yeah.
At the moment, there are not questions from the auditory. Don't be shy, please. Send your question in the chat. I think that Douglas will be open to answer to all the questions. If there are not questions, I go on with my personal. Well, you talk about for example, for insulation in buildings, or for very heavy construction, in particular for passive insulation from railway or train, induced vibration, and so on. I will ask if you design also vibration insulation system for example, vibrating machinery. So, for example, machinery or equipment that vibrates, and you can design also some kind of system for to insulate vibrating, for example, also in this case, a sensitive machinery or scientific equipment, for example.
So I have an answer to both questions. So we've isolated tons of sensitive equipment with air springs. And one of the largest projects we ever had was Nanyang Technical University in Singapore. And they wanted to have a isolated chamber that had no vibration, and they were right near a highway. They were near one of the main highways. It wasn't rail, it was highway. And when large trucks coming from the port and going past the school were measured, there was impact noise that was getting to the location of this high level chamber. And the idea was to utilize air springs to eliminate any problem. They were studying electrons at 0 degrees Kelvin. So that's as cold as you can possibly be, right? And what happens to electrons in that environment is they no longer move randomly, but they move only in 2 planes. So they were trying to analyze electrons with an electron microscope, a coordinate access measuring machine, and some other highly sensitive device, so that they could figure out what electrons will do at certain temperatures and how it will enhance medical applications and all sorts of things. So the bottom line was that isolation base was supported by air springs designed for 3/4 of a hertz, and they were about 1 meter in diameter. There was a dozen of them. The chamber was lined with copper and operated at that low temperature. And that's a whole other discussion because we've done military applications similarly.
Okay.
Both in Switzerland and Australia and in the US. And it's something that we have the capability of isolating really sensitive machinery. When you mentioned, do we isolate vibrating equipment? Yes, and that's normally for the mining industry. And we have isolated the belts and the components of the mining shake tables that eliminate certain types of elements in their slurry. So we have been involved in that in the mining industry, and not too many other places. But although I'm here for 42 years, you know, I can only recall what I've worked on, and there's many other people who could probably add to that.
Thank you. There are not questions for the audience. No, there is Darren Baxon. He said, "Hi, Douglas. I don't know if you, Douglas."
Yeah, I can see it.
Okay. So don't read. If you want to answer directly to Darren, please, the floor is yours. Please.
So that happens to be a wonderful question. We do all the bearing designs in-house. It's our specialty. We don't use an outside structural engineer to do anything. The shape factor curves that we've included in one of the shape factor curves, we generate them ourselves for the mixture of natural rubber that we have. So the big issue becomes, you have to understand shape factor, which is this design component of the bearing, which is the loaded area over the escape area. And you have to understand where the line is drawn with overloading. So we'll normally not have deflections in excess of 8% of a bearing thickness because we want to maintain low stress, low strain design. So all of it is done in-house. We do nothing with external software. We have some internal software that we utilize, but at the end of the day, when you design the bearing based on the shape factor for the compound that you're using, and then you test it and achieve the calculated result through the independent or the testing result, and it's then that bearing that gets independently tested yet again, and that is how we achieve the 100-year guarantees and warranties. So it's all in-house. It's all our information. I don't say it's proprietary, but we don't really give it out very often.
Okay, thank you, Douglas, and thank you, Darren, for your question. There are other questions from the audience. We have a couple of minutes. If there are another question, just one question, but probably I asked you probably the same question that I posed you. I asked you the last year, but I started to don't remember well. Sorry. You have shown that you perform. You talk about the static test and so on. You perform also dynamic test on your.
Absolutely.
Okay.
We test the natural frequency of the bearings with dynamic testing.
Okay.
We can find out the dynamic stiffness correction factors, which we've done for all our bearings, and we do shape table testing on a regular basis. For the state of California, we just finished shape table testing a floating floor design with the intent that in the state of California, there's a part of the government, it's called OSHPD, the Office of Statewide Health Planning and Development. It's now changed to HKAI, HKAI. I don't remember what that one acronym is. But the idea is anything that goes into hospitals have to be tested and seismically certified. So we put a floating floor sample on a shake table, and tested it dynamically to see its response to the actual input information for the earthquake, but also the structural integrity of the design. So ongoing testing is just simply a way to achieve education. I mentioned the work we've done at the University of California at San Diego. Shake tested a 10-story building with some of our equipment on it. And the idea is all that testing adds up to a library of what the capabilities of the company are. And we don't publish it, but we probably tested everything you could ever imagine 100 different ways, and it's our way of staying ahead of the curve.
Thank you very much for your answer. I think that now there are not other questions from the audience. And I don't know, Simona, if probably we can close the meeting. I would just thank Douglas for his very interesting presentation. I thank the attendees. There are more or less 30 persons at the end of the day. So it's a good, I think it's a good webinar. So thank you again, Douglas, and see you in Perugia next year for the conference of Acoustic Italian Association. And thank you again. And I let the floor to Simona to close the meeting today. Thank you again.
Thank you, my pleasure. Always welcome to do these type of things with the Italian Acoustical Society. Thank you for inviting us.
Thank you.
Thank you, everybody.
Take care. Bye-bye.